is given by 1/2 over ax squared plus bxy plus 1/2 over c y squared. And as we have seen at the beginning of the class today, is that the curvature, at least at the 0 point, is given by, in terms of the fundamental form, by a v1 squared plus 2b v1 plus c v2 squared. So that's the general expression for v1 and v2. So that what is now like the picture is that we have some x, y coordinates, and then our surface is given by the graph of some function. And now what this construction here says, we can rotate in the x and y direction. We can like rotate that by some angle, such that this middle term here vanishes. So rotate the x, y axis so that in a new coordinates b equals to 0. So that's always possible. If you like have like a function, you take the second derivatives, you end up with some b, and then you start rotating, and like you see how these second like the Taylor expansion up to second order changes under the rotation. You see you get some equation essentially for the angle, and then you solve that to always get like one of these b's to 0. And once we have that, then we can read off that that A and C are the principal curvatures. Then A equals to kappa 1 at 0 and C so in other words, surface is locally described as like the so if you have a surface, and that actually happens like universally, if you have some surface, you always find some local coordinates or some small patch where you can describe that as a graph. And then if you have the graph, you rotate in the axis a little bit until you end up with something that doesn't have like these mixed terms. And once you have like accomplished that, you can read off immediately the principal curvatures from that expression here. So that's one way. And the other way, of course, that gives you automatically some idea that once you know kappa 1 and kappa 2, you know how your surface looks locally around that point. Like it is like in second order, my surface goes in kappa 1 direction, it goes like x squared, and in the y direction, it goes like y squared, and both of these ones with the prefactor of kappa 1 and kappa 2, giving you like if they're like how much they are like parabolic and in which direction they are parabolic. So that's gives you a complete description of the local, local description. of the surface in terms of kappa 1 and kappa 2. So that's a little bit different, like in the same spirit as what we had for curves, where we also had like a theorem, which was the fundamental theorem of curves, was saying that once you know the curvature of function and the torsion function, you can reconstruct the whole curve. And that, like, it's a little bit of the same spirit that says, like, once you know the curvature, the principal curvatures, which are two functions, then based on this information, what you can give is at least like locally you can reconstruct the surface. So that means until second order at least, the principal curvature tells you all the information that there is to the surface. And if you have like an expression like that, then of course it depends very much, like this local behavior of the surface depends very much on what happens to kappa 1 and kappa 2. If they're like aligned, like if both of them positive, then you get like a valley in some way. If one of them is positive and the other one negative, you get like one of the saddle points. So that's like important, and actually that's the next definition is to give these points then like special names depending on how the surface looks locally around them. That's the next definition. Point P, the surface is called, and now three words. The first one is umbilic. So umbilic is like a Latin word, and it means navel. So like here, the point in your tummy. So that's a point by definition where kappa 1 of P equals to kappa 2 of P, which is equivalent to saying that kappa P of U is independent of U. So in each direction it looks like the same. And that's a bit like this idea that you have with the navel is like, like it's just like a hole, and like there's nothing, no particular direction that is preferred. One example we have already seen of that is the sphere. On the sphere, every point is an oblique point because the curvature in both directions were always -1. So that's every point. So that's the case of an oblique point. And now we have elliptic, parabolic, and hyperbolic. And this one of kappa 1 P and kappa 2 of P have the same sign. But are not equal to each other. Because otherwise you end up in the umbilic case. So in that case, if you look at the local form, you have kappa 1 and kappa 2 are like the same, and then what you end up with is something that looks like a hill for example, or like some valley where it's like in both directions you go like down to the point. So it's locally convex. So it's something like of that form, where it falls in both directions. See. So that's an elliptic point. Then we have the case where kappa 1 and kappa 2 of P have opposite signs and are not are not zero, or like none of the directions. So in that case, we have like one direction, we have like a square, and the other one is going up in the other directions. So that's a saddle, like where we have one direction, it goes down, and then we have the upper direction, it goes up. So that's a hyperbolic point. And then the parabolic point is if one of them is 0. And that's, but not both, otherwise we end up again in the umbilic case. So that would be, for example, on a cylinder. So it's like in one direction it's like falling, or like going in the other direction, and in one direction it's flat. So it's flat in one direction, and then it's curved in the other direction. So that follows directly from this equation, which says like locally it's described by a function, and kappa 1 and kappa 2 directly give us the expression for that. Just like some general remarks about these kind of points. Remark is usually, it's not really like that, but or not always, but the usual picture is as follows, is that, so if that's our surface, then usually what happens is that you have some direction where we have parabolic, and that's usually separates something from elliptic and hyperbolic. And then in a hyperbolic setting, you have isolated umbilic points. So that's the usually picture that you can like expect. It's not always the case. For example, the sphere is an example where everything is an umbilic point, and there are special other cases where this is also not holding. But that's the general picture, is that like usually you have like the parabolic as a separation between elliptic and hyperbolic, and then in the elliptic C you have some special points where you have like they are isolated and they are umbilic. So that's the general idea. Just as a general idea, a few more remarks is that on the torus, it's exactly like this with like no umbilic points. So on the torus, maybe that's a, yeah, let's make that like the question for the break. So if you have the torus as, it's very hard to draw a torus on the blackboard. So on the torus, what are the elliptic points, parabolic points, and hyperbolic points? And my homework is to, in the break, to make that picture nice. And you think about like what are the parabolic points, the hyperbolic points, are there umbilic points on the torus? And then we continue in 15 minutes, which would be yeah, let's say 20. So 7:20, and then someone of you might like give some ideas about like what are the umbilic points on the torus, the elliptic points, the hyperbolic, and the parabolic points. Okay, then see you later. I tried that again.
This is the second structure question that we were given in the last lecture. Now I want to translate into the matrix form. So first I need to change these two terms order to the index j and connected. So there will be a minus in front of it. But the equation we give in the homework is like this. There is no minus. I need to know which one is correct. Translate it into the matrix form. It's change their order. There will be a minus.
What do you mean by translated and matrix form?
This form is the element in the matrix. So when I want to translate into a matrix form, I need to write it like this. And then this is the row and this is the column. According to the times viewer of the matrix, this index will be connected with this index. So we need to change their order first. So there will be minus so I see it should be omega which minus omega which omega plus d omega. But the question you wrote in the homework statement is like this. There is no minus.
Okay. I don't have like the homework at the moment.
Homework statement.
Second.
Because the answer is also this two terms is in both zero, so there's no interval.
Yeah. So in that sense, yeah, I should have maybe been precise and really what it was like indexes. So yeah, like that was really just like a short-term notation for that equation. So you're right, like I was like definitely not precise enough that I meant like this equation, like when I wrote this equation here, I meant like this original equation.
This is connected.
Yeah, so it's like really like I wrote this one, but like what I meant was this. So I should have like wrote it with like the indices and with the summation there to make it more precise. So I was like too lazy and just like.
So which one is correct?
This one.
This one is correct.
Yes.
Oh, so this one you showed in the lecture has something wrong. And this is the equation you have shown in the lecture.
Okay, I mean then this one.
This one is correct.
Yes.
So there will be a minus.
Yes, so this one is here. That one is like I should have like instead of writing this, I should have wrote this. Yeah, so I was just like too lazy. I thought like, like when I wrote this one, I meant this one.
Yeah. You ignored the exchange.
Yes, I ignored like the indexes, but yeah, I should have not. Yeah, thanks for the feedback.
I don't know. I just drew this is a vector.
Yes.
But this is a vector function,
Yes.
and this should be a matrix. The question is, how can we derive this equation from this equation?
Yes, that's that.
For each I and J, this one is a vector.
Yes.
This one is not a number, so it is not a matrix, right?
I mean, you have like I something like that, right? So if you take now like x and x, you end up 0, 0. So it's like for every x, I, and j, you end up with a vector.
And so the shape operator has the chart.
Okay, let's continue with the torus. So what are the, let's start with the elliptic points. What are the elliptic points on the torus? Yes, so the outside part, if you're that part, like if you're just like have like a, maybe it's like nice, if you just like take the circle, it's a matrix, or like the outside part is elliptic. It's like the example, like what we have to see here is the elliptic points are the ones where they have the same sign. So it looks like a hill. So like if you go in this direction, you say like you fall, and then in these sides you also fall. And it's like you can imagine a little bit like being on some rift on a mountain, and you like fall in this direction and you fall in this direction. And that's like what happens, for example, here in that point. If you stay like outside here, you go around in this direction, like so. You have like in a local environment around that point. It looks like that it goes like this, and it also goes like this. So that's a elliptic point, and that same argument continues to hold like this. What are the hyperbolic points? Yes. So the hyperbolic points are the points where like these inside points. Are you looking for something? Or? Okay. So the hyperbolic points are the inside of the torus. So there are no parabolic and no umbilic points. What is that? Okay, and what are these points? Like the circles? Yes, and what are they? Are they parabolic or umbilic points? Yes. Like these points here, this one and this one, it's parabolic. So if you draw it on you have like a line that goes on top of here. This one side is elliptic. Then on top of the ridge, you have like nothing, no curvature in the direction if you keep going straight on and then you fall off in one of the sides. So these ones are the parabolic, and then like the inside are the hyperbolic points. So that's one of the examples of this exact phenomenon, is that you have hyperbolic points, the inside, then you have some boundary which are parabolic points, which are like the two circles up and the lower side, and then you have elliptic points on the other side. So in particular, the torus doesn't have any, there are no umbilic points. Without proof, it's the statement that but every other compact surface with no holes has at least one umbilic point. And there's like actually an open conjecture which says that every compact convex surface has at least two umbilic points. So that's an open conjecture that like no one knows how to solve. So if any one of you has some ideas, please let me know. So it like shows you that like it's like a very like natural question. Like okay, you see like they are usually isolated points, and then you would like to know how many of them are there. But like even things like this, like saying like finding a lower bound is like very complicated. But usually they are like isolated points in a sea of elliptic points. Okay. So now I would like to go towards like describing the behavior around an oblique point. But before we come to that, I need to introduce a little bit of more notation. Which are very much related to the principal directions. So two definitions. First of all, a frame which is adapted to S is called a so-called Dabou frame. Dabou frame. So Dabou was a French mathematician. If E1 of P and E2 of P are the principal directions. At P. So like a Dabou frame is like a special frame which says like that at least like that E1 and E2 are like these eigenvectors of the shape operator. So if you apply the shape operator now in these coordinates or in these frames, then they are nicely diagonal matrix, and then they are called a Dabou frame. And similarly, a unit speed curve C is called a line of curvature if C dot is always the principal for example, instead C of t equals u1 at the point C of t. So you have like a curve that always goes in the direction of maximum curvature or minimal curvature, but like really gives you always in the principal directions. And you call it a line of curvature. There's a theorem which I will not prove, and so you can look at, for example, to Camo, which is like 3.4.4, or in O'Neill, I think it's lemma 6.2.5, if you're interested in the proof, which says that away from umbilic points a Dabou frame always exists. So like locally, if you're not like around an oblique point, then you find always a frame, which is nice and has this property that one of the axes goes in the E1 direction is always one principal direction, and then E2 is the other principal direction over the whole patch. And one thing is like to notice is that if you have like, for example, two lines of curvatures, because and they are like one of them is in U1 direction and the other one in U2 direction, what you always have is that they have to intersect orthogonal, because U1 and U2 were always orthogonal at each point. So if you have like two curves which intersect at some point, then they have to intersect orthogonally. So that allows you to actually think about that construction here of the Boole frames now in terms of like a bit more applied things. For example, you can apply it for architecture. And before I come to that, I also want to discuss like how you can like visualize the lines of curvature near an oblique point. So here we have an oblique point which is always in the center. These are it's always the oblique point, and then you think about, okay, like the oblique point was like special because it's like the curvature of directions was like always like there's no special point direction in the from the curvature perspective. But of course, you can like say like, for example, the curvature gives you the second order Taylor expansion, and then you can think about, okay, what further information is there like for the third order, and that gives you then also some information. And you can visualize Forstern into three different classes, and these are called the star, the mon-star, also some counts the mon-lemon. It's like a bit of and the lemon. Yeah, like the star, I think it makes sense because it's like really like you see from the pattern, it looks like a star. And the lemon, it's a bit like because you have that on an ellipsoid or on a if you just like buy a lemon in the supermarket, then and you draw the principal curvature lines or the lines of curvature, then it looks like that on some patches. So that's why it's called a lemon. So these are like the cases what can happen. So like on each picture, like the blue lines are say like, I don't know, like plus or minus, but say like these are the lines of the curvature kappa 1, and then the red ones are always orthogonal, and they are the lines of curvature where we have kappa equals to 2. And then you see like there are different kind of behavior. We have like, for example, here they go like in a star formation. Here you have something like a half star, where you see here this one goes like in a star, and then here a star is coming in some way, like the blue lines here. Like here you have like 3 inputs, red, and 3 inputs blue, but here you have like 3 of them are coming from the same directions. And here they don't really meet, but it's more like that they overlap. So that's like essentially like the only patterns that you can have near an oblique point. So it's like the idea that is like, okay, these oblique points are special. And if you have special points, then usually it's like a good idea to first say like, try to answer how many are there, or like find conditions that ensure that they exist, but we have seen that it's really hard. And the next step would be, okay, once I know that there is an oblique point, I would like to understand how it looks like around that point. And that's like completely answered by these questions, where you say like, okay, that's like the only 3 possible cases that you can have near an oblique point. It's not super important. I just wanted to show you that there is like more things that you can go after, like knowing that you have an oblique point. Some applications of like this line of curvatures are like really in a computer visualization, for example, where you say, okay, you have like some model of some object, like here say like you have a car, and you would like to put some texture on it or something of that form. So you would like to have some kind of grid on that car, and usually you need to have like more refined information if you have something where it's like curvature is high. So what you can do is like you start with drawing just like the principal lines of curvature. So like you find like these lines of curvature where you say, okay, you try to find like a curve that always goes in a principal direction, and then you draw these ones on your object. And then as a second step, you usually have to refine it a little bit. So that's a pretty irregular mesh. So you have to refine it a little bit, similar here. And then you get like a nice mesh or like a nice grid on your object that you would like to study and put like in computer graphics, which is adapted to the curvature. So you see like, just like by looking at this picture, you see that there are like certain regions of curvature, and they have like a grid which is adapted to the curvature. So that's like a nice application of like having this line of curvatures because they allow you to do a computer visualization with that. There are also applications in architecture, for example. Here's an example. I'm not sure if it was really constructed or only proposed. I think it was like for some, like one world conquest or something like that. Someone came up with this idea of having like a roof which has like very different curvatures. And there were different requirements on how to construct it depending on the curvature. So what they did, at least proposed, was to reconstruct or decompose the roof in two aspects, namely in an elliptic and in a hyperbolic points. So in architecture, they are called like single curvature and double curvature. Essentially, a single curvature means like they are curving in the same directions, and double curvature, you have like one this and one like the opposite. And then they said like, okay, because the reason why they did that was because from a construction viewpoint, there were really different requirements of what kind of like information you had to use or like what kind of materials and how to construct that, depending on if it's like curved like in both directions like this, or if one of the is differently curved. So you have to use different materials for the elliptic points and different materials for the hyperbolic points. So it's just like to show you that some applications of like these hyperbolic points or the elliptic points are coming from directions where you maybe don't expect them in the first, if you think about this for the first time. So that's some applications. Okay. So the next objective for the last time for today will be to express these principal curvatures in terms of these connection forms that we had before. So what we did before was like to express that the shape operator is like very much related also to the connection forms, and now we would like to find a connection between these kappa 1 and kappa 2 and express them in terms of the connection forms. So suppose we start with like a taboo frame. So E1, E2, and E3 is a taboo frame. On S. So that means we have S applied to E1 equals to kappa 1 E1, and S applied to E2 gives you E2. Where everything should be read like for each point P, we can evaluate both sides. So hence, if you calculate the fundamental matrix of the second fundamental form, so that's where we plug in E1, EI, and EJ in the second form, what we get, which is by definition is just EI times the shape operator applied to EJ. So that's always just like EJ scaled with kappa j again. So it's the diagonal matrix with entries, just kappa 1 of P, 0, 0, kappa 2 of P. And moreover, because we know that the connection forms are related to the shape operator, we also see that we can calculate the can calculate these expressions for the omega 1 and omega 2. Essentially, that follows from the equations that we had like last times, just like plugging in now that E1 is like proportional to the S1. So we get the following equations for these connection forms in terms of, because essentially that's like the coordinates are like these, the frames there. Okay, so let's take d of that and see what comes out of these expressions. So take d, like the exterior differential. So what we end up with is that d omega 1 free equals to d kappa 1 wedge theta 1 plus kappa 1 d theta 1. So that's the statement. And then on S, so we restrict these expressions on S. We can write this one as omega 1, 2, omega 2, 3. And similarly here, we can write it as omega 1, 2, wedge theta 2, as if you have like these ones and you restrict it to S, you get 0. So we can solve for this expression. So d1 kappa 1 phi 1